at EWCA. This is for higher level. Actually, it's for level 6, 7, 8, 9, 10. My teacher Frank, and today's lesson we'd like to discuss computational thinking for the professions intro. So essentially, we'll be running by 7 topics, which means we'll be also looking into 7 activities. The objective is for you to be able to describe and illustrate a content-related concept. What is the impact of computer education on your income? Will it actually grow your income and make you richer? We'll see. Can you draw a diagram explaining how humans talk with computers and how computers talk with humans? How do we actually talk with the computers if they're just plain not human beings and they can still understand us? We'll try to figure that out today. Now, draw a rough timeline of how modern day computers up to year 2020, if you can, develop from written history. Write your own name using the binary code language. Flowchart and how you prepare for online class. Actually, let me change that. Flowchart of how you choose your lunch. Choose your food for lunch. Let's make it simple. You have a month to do this, a project to design a game through a Scratch program. Now, this is a group activity. So, it's also time for today. We'll use the time today to actually get your partners to minimum. And students should be able to convey clearly how differently computer scientists think. And hopefully at the end of this class that you are able to actually think like a computer scientist. Okay, first up. Now, I'd like to focus on 3 countries. The Philippines, which is there. And Congo, which is here in Africa. And Monaco. Monaco is there. Right? So 3 countries of varying sizes. The richest country actually is Congo. It has the most number of treasure, gold, mineral, copper in there. And then you got the Philippines. And then Congo is a very small island just off Italy. It's a French island below Italy in the Mediterranean Sea. Now, let's take a look at the impact of computer education on income. So if you look at Monaco, it's $15,507 per month. That's how much, on an average, a person actually earns in Monaco. In the Philippines, it's only about $321 per month. And Congo is about $43 per month. Now, let's take a look at what they actually produce. What do these countries actually sell to warrant such kind of salary? Now, the expert here is mostly financial services and scientific technical activities, so pharmaceuticals. So they develop medicine for people, and they're very, very good at scientific activities, and they have financial services too. So banks and money. For the Philippines, our experts are IC, integrated circuits, so a little bit advanced, but still not that advanced. But we have very basic electrical machineries that we use, and insulated wire and cable. And for Congo, we've got gold, diamond, and copper. So very, very raw materials that they're actually selling. In terms of job opening, for CTO, Chief Technology Officer, $4.8 million per year. That's how much a CTO earns on an average in Monaco. Critical skills would be PHP 7, MySQL, Symfony, and then you've got your character skills, team spirit, synthesis, analytical skills, adaptability, priorities management. In the Philippines, you've got the same CTO, and $2.3 million per year. That's how much. So it's not far. It's half the salary of a CTO in Monaco. So it does have an impact. On an average, a person earns $321 only, or about 10,000, 11,000 pesos. But if you're a CTO with a tech skill, you can still earn as much as $2.3 million per year. Java Plus and DigitalOcean, which is a networking language that you need. You also need a bachelor's degree, and you need to be very strong in planning analytics, communication skills, and evaluate processes effectively. So these are things that we're actually learning at EWCA, and we're training it to do that. But let's look at Congo, and there's no job opening for CTO there. And that's probably why they're actually earning $43. Now, activity 1, section 1. What is the impact of computer education and skills on income? So based on this discussion, cite your observation on Monaco, Philippines, and Congo. And is there an impact of computer education and skills on income? And what is the impact? So I want you to answer that in your own words and put that in your notebook or your worksheet. All right. Put a pause on this video, and once you're ready, completed with your activity 1 answer, you can proceed. Activity 2.
Do you remember when you first realized that your computer was more than just a monitor and keyboard? That between the mouse click and the video playing, there was something that captured your attention, understood it, and made it real? What is that something? Is it gremlins? Let's imagine that we can shrink down to the size of an electron and inject ourselves into a click of a mouse. If you took your mouse apart, you'd see that it's really a very simple machine. It has a couple buttons and a system for detecting motion and distance. You might have an optical mouse that makes these measurements with lights and sensors, but older ones did this with a hard rubber ball and some plastic wheels. Same concept. When you click the button on your mouse, it sends a message to the computer with information about its position. When your mouse click is received, it's handled by the basic input-output subsystem. This subsystem acts like the eyes and ears and mouth and hands of the computer. Basically, it provides a way for the computer to interact with its environment. But it also acts like a buffer to keep the CPU from being overwhelmed by distractions. In this case, the I/O subsystem decides that your mouse click is pretty important, so it generates an interrupt to the CPU. Hey CPU, gotta click here. The CPU, or central processing unit, is the brains of the whole computer. Just like your brain doesn't take up your whole body, the CPU doesn't take up the whole computer, but it runs the show all the same. And the CPU's job, its whole job, is fetching instructions from memory and executing them. So while you're typing, maybe really fast, like 60 words a minute, the CPU is fetching and executing billions of instructions a second. Yes, billions, every second. Instructions to move your mouse around on the screen, to run that clock widget on your desktop, play your internet radio, manage the files you're editing on the hard drive, and much, much more. Your computer CPU is one heck of a multitasker. But oh my gosh, there's a very important mouse click coming through now. Let's drop everything now and deal with that. There are programs for everything that the CPU does. A special program for the mouse, for the clock widget, for the internet radio, and for dealing with letters sent by the keyboard. Each program was initially written by a human in a human-readable programming language like Java, C++, or Python. But human programs take up a lot of space and contain a lot of unnecessary information to a computer, so they're compiled and made smaller and stored in bits of ones and zeros in memory. The CPU realizes that it needs instructions for how to deal with this mouse click, so it looks up the address for the mouse program and sends a request to the memory subsystem for instructions stored there. Each instruction in the mouse device driver is duly fetched and executed. And that's not nearly the end of the story, because the CPU learns that the mouse was clicked when the cursor was over a picture of a button on the monitor screen, and so the CPU asks memory for the monitor program to find out what that button is. And then the CPU has to ask memory for the program for the button, which means that the CPU needs the monitor program again to show the video associated with the button, and so it goes. And let's just say that there are a lot of programs involved before you even see the button on the screen light up when you clicked it. So just the simple task of clicking your mouse means visiting all of the critical components of your computer's architecture. Peripherals, the basic input-output system, the CPU, programs, and memory, and not one gremlin.
About how computers evolved from electromechanical devices that often had decimal representations of numbers, like those represented by teeth on a gear, to electronic computers with transistors that can turn the flow of electricity on or off. Unfortunately, even with just two states of electricity, we can represent important information. We call this representation binary, which literally means of two states, in the same way a bicycle has two wheels or a biped has two legs. You might think two states isn't a lot to work with, and you'd be right, but it's exactly what you need for representing the values true and false. In computers, an on state when electricity is flowing represents true. The off state, no electricity flowing, represents false. We can also write binary as ones and zeros instead of trues and falses. They're just different expressions of the same signal. But we'll talk about that in the next episode. Now, it is actually possible to use transistors for more than just turning electrical current on and off, and to allow for different levels of current. Some early electronic computers were ternary, that's 3 states, and even quinary using 5 states. The problem is, the more intermediate states there are, the harder it is to keep them all separate. If your smartphone battery starts running low, or there's electrical noise because someone's running a microwave nearby, the signals can get mixed up. And this problem only gets worse with transistors changing states millions of times per second. So placing two signals as far apart as possible, using just on and off, gives us the most distinct signal to minimize these issues. Another reason computers use binary is that an entire branch of mathematics already existed that dealt exclusively with true and false values, and they had to figure out all the necessary rules and operations for manipulating them. It's called Boolean algebra. George Boole, from which Boolean algebra later got its name, was a self-taught English mathematician in the 1800s. He was interested in representing logical statements that went under, over, and beyond Aristotle's approach to logic, which was unsurprisingly grounded in philosophy. Boole's approach allowed truth to be systematically and formally proven through logic equations, which he introduced in his first book, The Mathematical Analysis of Logic, in 1847. In regular algebra, the type you probably learned in high school, the values of variables are numbers, and operations on those numbers are things like addition and multiplication. But in Boolean algebra, the values of variables are true and false, and the operations are logical. There are 3 fundamental operations in Boolean algebra: a not, an and an or operation. And these operations turn out to be really useful, so we're going to look at them individually. A not takes a single Boolean value, either true or false, and negates it. It flips true to false and false to true. We can write out a little logic table that shows the original value under input, and the outcome after applying the operation under output. Now here's the cool part. We can easily build Boolean logic out of transistors. As we discussed last episode, transistors are really just electrically controlled switches. They have 3 wires, 2 electrodes, and 1 control wire. When you apply electricity to the control wire, it lets current flow through from one electrode through the transistor to the other electrode. This is a lot like a spigot on a pipe. Open the tap, water flows. Close the tap, water shuts off. You can think of the control wire as an input, and the wire coming from the bottom electrode as the output. So with a single transistor, we have 1 input and 1 output. If we turn the input on, the output is also on because the current can flow through it. If we turn the input off, the output is also off and the current can no longer pass through. Or in Boolean terms, when the input is true, the output is true, and when the input is false, the output is also false, which again we can show on a logic table. This isn't a very exciting circuit though, because it's not doing anything. The input and output are the same, but we can modify this circuit just a little bit to create a not. Instead of having the output wire at the end of the transistor, we can move it before. If we turn the input on, the transistor allows current to pass through it to the ground, and the output wire won't receive that current, so it will be off. In our water metaphor, grounding would be like if all the water in your house was flowing out of a huge hose, so there wasn't any water pressure left in the shower. So in this case, if the input is on, output is off. When we turn off the transistor though, current is prevented from flowing down it to the ground. So instead, current flows through the output wire, so the input will be off and the output will be on. And this matches our logic table for not. So congrats, we just built a circuit that computes not. We call them not gates, and we call them gates because they're controlling the path of our current. The and Boolean operation takes 2 inputs, but still has a single output. In this case, the output is only true if both inputs are true. Think about it like telling the truth. You're only being completely honest if you don't lie even a little. For example, let's take the statement, my name is Carrie Ann and I'm wearing a blue dress. Both of those facts are true, so the whole statement is true. But if I said my name is Carrie Ann and I'm wearing pants, that would be false, because I'm not wearing pants. Or trousers if you're in England. The Carrie Ann part is true, but a true and a false is still false. If I were to reverse that statement, it would still obviously be false. And if I were to tell you 2 complete lies, that is also false. And again, we can write all of these combinations out in a table. To build an AND gate, we need 2 transistors connected together so we have our 2 inputs and 1 output. If we turn on just transistor A, current won't flow because the current is stopped by transistor B. Alternatively, if transistor B is on, but transistor A is off, same thing, the current can't get through. Only if transistor A and transistor B are on does the output wire have current. The last Boolean operator is OR, where only 1 input has to be true for the output to be true. For example, my name is Margaret Hamilton or I'm wearing a blue dress. This is a true statement, because although I'm not Margaret Hamilton, unfortunately, I am wearing a blue dress. So the overall statement is true. An OR statement is also true if both facts are true. The only time an OR statement is false is if both inputs are false. Building an OR gate from transistors needs a few extra wires. Instead of having 2 transistors in series, one after the other, we have them in parallel. We run wires from the current source to both transistors. We use this little arc to note that the wires jump over one another and aren't connected, even though they look like they cross. If both transistors are turned off, the current is prevented from flowing to the output, so the output is also off. Now, if we turn on just transistor A, current can flow to the output. Same thing if transistor A is off, but transistor B is on. Basically, if A or B is on, the output is also on. Also, if both transistors are on, the output is still on. Okay, now we've got not and OR gates, and we can leave behind their constituent transistors and move up a layer of abstraction. The standard engineers use for these gates are a triangle with a dot for a not, a D for the and a spaceship for the OR. Those aren't the official names, but that's how I like to think of them. Representing them and thinking about them this way allows us to build even bigger components while keeping the overall complexity relatively the same. Just remember that all of the mess of transistors and wires is still there. For example, another useful Boolean operation in computation is called an exclusive OR XOR for short. XOR is like a regular OR, but with one difference. If both inputs are true, the XOR is false. The only time an XOR is true is when one input is true and the other input is false. It's like when you go out to dinner and your meal comes with a side salad or a soup. Sadly, you can't have both. And building this from transistors is pretty confusing, but we can show how an XOR is created from our 3 basic Boolean gates. We know we have 2 inputs again, A and B, and 1 output. Let's start with an OR gate, since the logic table looks almost identical to an OR. There's only one problem. When A and B are true, the logic is different from OR, and we need to output false. To do this, we need to add some additional gates. If we add an AND gate and the input is true and true, the output will be true. This isn't what we want, but if we add a not immediately after, this will flip it to false. Okay, now if we add a final AND gate and send it that value along with the output of our original OR gate, the AND will take in false and true, and since AND needs both values to be true, its output is false. That's the first row of our logic table. If we work through the remaining input combinations, we can see this Boolean logic circuit does implement an exclusive OR, and XOR turns out to be a very useful component, and we'll get to it in another episode. So useful, in fact, engineers gave it its own symbol too, an OR gate with a smile. But most importantly, we can now put XOR into our metaphorical toolbox and not have to worry about the individual logic gates that make it up, or the transistors that make up those gates, or how electrons are flowing through a semiconductor, moving up another layer of abstraction. When computer engineers are designing processors, they rarely work at the transistor level and instead work with much larger blocks, like logic gates, and even larger components made up of logic gates, which we'll discuss in future episodes. And even if you are a professional computer programmer, it's not often that you think about how the logic that you are programming is actually implemented in the physical world by these teeny tiny components. We've also moved from thinking about raw electrical signals to our first representation of data, true and false, and we've even gotten a little taste of computation. With just the logic gates in this episode, we could build a machine that evaluates complex logic statements, like if name is John Green and after 5 p.m. or is weekend and near Pizza Hut, then John will want pizza equals true. And with that,
Now it's time for you to talk to your computer. Based on the video that I just shared, can you draw a diagram of how humans talk to computers and how computers talk to humans? So it doesn't have to be a very complex diagram. It can fit this box. So, but I just want to see how your understanding is of how humans talk to computers and how computers talk to humans. It doesn't have to be written. You can draw if you like, but I'd like you to be able to draw a diagram. Oh, history of computers. This is a brief timeline. So this is how Charles Babbage designed a Victorian-era computer called the analytical engine. So it's still very mechanical at that time. It's a different computer that we have today, and this is actually a computer portion of the mill with a printing mechanism somewhere there. But first, let's look at 1801. In 1801, Joseph Marie Jacquard invents a loom that uses a punch wooden card to automatically weave fabric designs. So it actually started with fabric. Early computers would use similar punch cards in the future, but they actually wanted to, in 1801, they wanted to sort of make same clothes with the same design. And how do you do that very quickly? You use a punch card. In 1822, the English mathematician Charles Babbage conceived a steam-driven calculating machine that would be able to compute tables of numbers. This is funded by the English government, and it's a failure. And more than a century later, after 70 years, the world's first computer was actually built. In 1890, Herman Hollerith designed a punch card system to calculate the 1880 census, accomplishing the task in just 3 years and saving the government $5 million. He established a company that would ultimately become IBM. In 1936, Alan Turing presents the notion of a universal machine, later called the Turing machine, capable of computing anything that is computable, and the central concept of the modern computer was based on his ideas. In 1937, J.V. Atanasov, professor of physics and mathematics at Iowa State University, attempts to build the first computer without gears, cams, belts, or shafts. So it's starting to become electronic, but not there yet. It's 1937. And in 1939, Hewlett-Packard is founded by David Packard and Bill Hewlett in a Palo Alto, California garage, according to Computer History Museum. And who knows, maybe you can become the next big computer scientist, and you can actually devise something new just in your garage. Why not, right? 1941, Atanasov and his graduate student, Clifford Berry, designed a computer that can solve 29 equations simultaneously. This marks the first time a computer is able to store information on its main memory. In 1943 to 1944, two University of Pennsylvania professors John Mauchly and Presper Eckert built the Electronic Numerical Integrator and Calculator, or ENIAC. Considered the grandfather of digital computers, it fills a 20-foot by 40-foot room and has 18,000 vacuum tubes. Now, vacuum tubes are a very important invention. It's like our light bulb, and before, that's how data is transferred from the actual command to what's inside the computer through the vacuum tube. 1946, Mauchly and Presper left the University of Pennsylvania and received funding from the Census Bureau to build the UNIVAC, the first commercial computer for business and government applications. In 1947, William Shockley, Bardeen, and Breton of Bell Laboratories invented the transistor. They discovered how to make an electric switch with solid materials and no need for vacuum. So the modern day computer is now made by transistors, no longer the vacuum. And that's why and then we're actually making transistors smaller now. So now it can fit if you're working on your iPad now, that's how small the transistors are. It can actually fit your phones that are very, very small. 1953, Grace Hopper develops the first computer language, which eventually becomes known as COBOL. Computer language means that, it's a language that allows you and the computer to speak. Remember the principle that there's always a translation that's happening between you and the computer. The computer cannot actually understand you. They can only understand you through ones and zeros, or a switch off and a switch on language. And there's a million, a billion, a trillion off and on commands that are happening in your computer as you actually type something. So that's what's happening in there. 1954, the Fortran programming language, an acronym for Formula Translation, is developed by a team of programmers at IBM led by Jan Backus, according to the University of Michigan. 1958, Jack Kilby and Robert Noyce unveiled the integrated circuit, known as the computer chip. Kilby was awarded the Nobel Prize in Physics in 2000 for his work. 1964, Douglas Engelbart shows a prototype of the modern computer with a mouse and a graphical user interface, or what we call a GUI. This marks the evolution of the computer from a specialized machine for scientists and mathematicians to a technology that is more accessible to the general public. Before, it cannot be used by just the plain simple man on the street and woman on the street, but now computers can now be used, and thanks to the graphical user interface, you can now see everything what's happening behind the computer through our screen. 1969, a group of developers at Bell Laboratories produced Unix, an operating system that addressed compatibility issues. Written in C programming language, Unix was portable across multiple platforms, and that's why there's actually a language that's being used so that different computers can help you program and can be used to program software. 1970, the newly formed Intel unveils the Intel 1103, the first dynamic access memory DRAM chip. In 1971, Alan Sugar leads a team of IBM engineers who invented the floppy disk. We gotta save those files in the computer, and the floppy disk allows us to save all those programs. 1973, Robert Metcalfe, a member of the research staff for Xerox, developed Ethernet, for connecting multiple computers and other hardware. Ethernet is where internet actually came from. Before they just wanted to connect multiple computers. Now we can actually connect to computers everywhere in the world. This one is just connecting multiple computers in one location. Now we can connect through the internet in the whole world in multiple locations. So in 1974 to 1977, a number of personal computers hit the market, including Shelby and Mark 8 Altair, IBM 500, Radio Shack's TRS-80, affectionately known as the Trash 80 with the Commodore PET. So this is actually a great innovation, because in 1974 to 1977, you can now bring the computer to your home. Before, it's so big, you actually need a building to house a computer, and it can't even do as much as what you can do now with your personal computer. In 1975, the January issue of Popular Electronics magazine features the Altair 8080, described as the world's first mini-computer kit to rival commercial models. Two computer geeks, Paul Allen and Bill Gates, offer to write software for Altair using the new BASIC language. On April 4, after the success of this first endeavor, the two childhood friends formed their own software company, Microsoft. 1976, Steve Jobs and Steve Wozniak, two Steve, started Apple Computers on April Fool's Day and rolled out Apple I, the first computer with a single circuit board, according to Stanford University. In 1977, Radio Shack initial production run of the TRS-80 was just 3,000, and it sold like crazy. For the first time, non-geeks could write programs and make a computer do what they wished. And so today we'll be learning more about programming using the Crash online software and you have a month to be able to use the Crash software to design a simple game. 1977, Jobs and Wozniak incorporate Apple and show the Apple II at the first West Coast Computer Fair. It offers color graphics and incorporates an audio cassette drive for storage. So in 1977, that's when colored computer was first featured. In 1978, accountants rejoiced at the introduction of VisiCalc, the first computer spreadsheet program, maybe the basis of our Excel spreadsheet now, and what your parents probably use to compute their funds, their reports, their finances using the Excel spreadsheet program. 1979, word processing becomes reality as MicroPro International releases WordStar. I have used this as a young kid, but I don't think you're going to use that anymore. You have a more advanced software. 1981, the first IBM personal computer code named Acorn is introduced. It uses Microsoft's MS-DOS operating system. It has an Intel chip. 2 floppy disks and an optional color monitor. This is my first understanding of how a computer looks like. In 1983, Apple's Lisa is the first personal computer with a GUI. It also features a drop-down menu and icons. So it's marketed as a flip form factor and probably your first laptop. 1985, Microsoft announces Windows according to Encyclopedia Britannica. Commodore unveils Amiga 1000, which features advanced audio and video capabilities. You can actually now watch films and audio in your computer. 1985, the first .com domain name is registered, and World Wide Web would mark the formal beginning of Internet history in March 15. The Symbolics Computer Company, a small Massachusetts computer manufacturer, registers Symbolics.com. More than 2 years later, only 100 .coms have been registered. In 1986, Compaq brings Desk Pro 386 to market. Its 32-bit architecture provides a speed comparable to mainframe. So it's actually a very small computer now that can fit on your desk, but it used to be a mainframe, meaning it's a computer that is as big as a building, but now with a 32-bit architecture, it's pretty fast for a small computer. 1990, the Tim Berners-Lee, a researcher at CERN High Energy Physics Laboratory in Geneva, develops hypertext markup language HTML. It is a language that can be used now for World Wide Web, and that's why through HTML you can put something online, draw something online, put an image, click play, and it will play through the HTML markup language. 1993, the Pentium microprocessor advances the use of graphics and music on PCs. In 1994, PCs become gaming machines as Command & Conquer and Magic Carpet, The Descent, Little Big Adventure. Some other games hit the market. What are your favorite games? I'm curious. So 1994 was the start of PCs becoming gaming machines. 1996, before there was actually just Game & Watch, but now PCs now become more of a gaming machine. Now, 1996, Sergey Brin and Larry Page developed Google search engine at Stanford University. 1997, Microsoft invests $150 million in Apple, which was struggling at that time, ending Apple's court case against Microsoft, and Microsoft copied the look and feel of its operating system. 1999, Wi-Fi becomes part of the computing language, and users begin connecting to the internet without wires. In 2001, Apple unveils the Mac OS X operating system, possibly where computers are now running in, like my computer. And Microsoft rolls out Windows XP, which your mom and dad's computer may be running in as well, and redesign the GUI. In 2003, the first 64-bit processor, AMD's Athlon 64-bit, becomes available to the consumer market. So it used to be 32, now it's 64, and that's why the language, the binary code in it, is actually 64 bits. So there's actually more numbers and more codes that you can put in one single chip. And that means that you can have a faster way to program. In 2004, Mozilla's Firefox 1.0 challenges Microsoft Internet Explorer, the dominant web browser at that time, and Facebook, a social networking site, launches. I didn't have Facebook until 2007, so that's history for me, a new history lesson for me. 2005, YouTube, a video sharing service, is founded, and in this class, you will be asked to also create your own YouTube page, but only in 2005 was when it actually started, and Google acquired Android, a Linux-based mobile phone operating system. So who would have thought, that YouTube in 2005 would actually change life at this point, 2020, 15 years later. 2006, Apple introduced the MacBook Pro. It's the first Intel-based dual-core mobile computer, as well as Intel-based iMac. Nintendo's Wii game console hits the market as well. In 2007, iPhone brings many computer functions to the smartphone. In 2009, Microsoft launches Windows 7, which offers the ability to pin applications to the taskbar and advances in touch and handwriting recognition, among other features. In 2010, Apple unveils the iPad. Do you have an iPad? Raise your hand. And 2011, Google releases the Chromebook, a laptop that runs the Google Chrome OS. 2012, Facebook gains 1 billion users, and it changed life ever since. I can't find anyone who's not on Facebook anymore, except maybe for a few, but Facebook is sort of the new room for me to contact everyone. 2015, Apple releases the Apple Watch computer right in your wrist, and 2016, the first programmable quantum computer was created. Until now, there hasn't been any quantum computing platform that had the capability to program new algorithms to the entire system. They're usually each tailored to attack a particular algorithm, so this is something new. And 2017, the Defense Advanced Research Projects at agencies developing the new molecular informatics program that uses molecules as computers. Chemistry offers a rich set of properties that we may be able to harness for rapid, scalable information storage and processing. That's according to Ann Fisher. And the richness of structure, each molecule has a unique three-dimensional atomic structure, as well as variables such as shape, size, or even color. And this richness provides a vast design space for exploring novel and multi-value ways to encode and process data beyond zeros and ones of current logic-based digital architectures. So who knows, maybe computing using molecular informatics can make you download stuff in just a second. A very, 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 very big file in just a second. Make it draw very quickly in a second. And that is what we're actually trying to explore. So what I'd like you to do is actually create a timeline diagram of the history of computer using this session. Okay, you can now pause the video and work on your worksheet. Activity 3. Now I'd like you to, let's change this to history of computer. So activity 3 is, I would like you to draw a diagram of how computers evolved from written history. So based on my discussion earlier from 1800s to the development of modern computer based on your understanding of our discussion today. Next up would be the binary code. So this is how the binary code looks like. Remember earlier we discussed that the computers cannot actually understand you if you say turn it, turn off or switch off, or it cannot understand you to add two things together. All right, or when you write your name and it actually reflects your name, it doesn't actually understand that. It can only understand 010110. So this is the binary code that your computer understands, and based on these codes, it actually helps it understand what transistor has to be switched off and switched on, and then it returns something on your screen based on the command that you actually put. So activity 4 is write your name using the binary code. So based on this, I want you to put in the numbers to write your name or even your nickname. Okay, you can now hit pause, and then you can play it again, hit play again once you're done. Right, next up would be flowcharts. Flowcharts actually allow you to organize your world, not only the physical world, but also in the computer world. Now, how it looks is it's represented by different shapes. And it starts with this oval shape kind of thing. It also ends with that, right? And if it this rectangle represents action or process, this one represents a document that you need, this one represents a decision, input, output, circle, connector, flow line, delay, and merge. So how is it used? So let's say you're planning your lunch. You're planning to have lunch on Sunday. And so it starts with you are hungry. So that's the start and end. Then you would ask the question, is mama at home? So that's the decision that you have to make. If yes, you will enjoy your lunch, and that's the end, right? Is mom at home? No. Look for food in the fridge. So that's action or process because you're looking for food. There's an action, add 2 cups of flour, so something like that. Then then you would make a decision in the fridge. So another diamond. Anything you want to eat? Yes. If yes, then you enjoy your lunch, right? If no, then you do another decision. Feel lazy to go out? Then you make a decision again. It can be I want to go out for some fresh air. All right. So then you make a decision again, and action or process. Find a restaurant. But if you don't want to do that, yes, I'm very lazy to go out. Feel lazy to go out? Yes, I'm very lazy to go out. Then you order takeout. Then these two will make for a merge. It will merge here to another decision. Anything you want to eat? No. And so if you didn't eat anything anyway, then you stay hungry. But anything you want to eat, and the answer is yes, then you actually enjoy your lunch. So this is the flowchart for how you troubleshoot the computer. You start, then make a decision. Diamond, yes and no. No, power light on. Let's say your computer doesn't want to start, right? So yes, error message. There's a decision. Yes. If there's an error message, yes, then you perform diagnosis, and then you turn on computer again, and then if it's yes, if it's no, then you check if the power light is on, then yes. So let's say yes. So start, computer on, and then if it's not turning on, then you go to no, and then is the power light on? If the power light is not on, then no. Then check if the power is plugged to the wall, and if it's no, then plug the power to the wall, and then start again. Right now, if your answer is yes, computer on, yes, and there's an error message in your computer, then yes, you perform a diagnosis and then computer on. Now, if your answer is computer on, yes, there's an error message, but there's no error message, and computer's in good condition, and then that's the end, right? So that's good. So start, computer on, no, power light on. We already answered no. So let's say the answer is yes. Then you find a specialist to help you, but this one doesn't have a movement. Oh, then actually you have to put a line there, and that's the end, and so you put an arrow there and end. So that's how you do your flowchart. If you have any questions, let me know. So activity 5, draw a flowchart of how you decide what to eat for breakfast. Very simple. So I'd like to see all the elements in there: start, action, and your decision. Feel free to use other things. Maybe you need a document or a connector, but I want to be seeing the flow line, the action process, the start and the end, and the decision there. Right? Next.
Website address. Or you could also just type in Scratch on Google. And here's how you spell Scratch. SCRATCH. So here are the 2 options of how you can program on Scratch. The first one is you're going to program online, but you'll need, just search it up on Google, and then, yeah, as I said, like on the link saying how to spell Scratch, do that, and then online, you have to have the internet, but here's the other version, Scratch Offline. Scratch Offline, you have to download and install the app, and you don't need the internet for it. So let's start with Scratch Online. Click Join Scratch, and then you'll see the form that you have to fill out next. Your username can be anything, but if it comes up to you that the username already exists, then just pick another username. Then remember the password and type it in. Then press the next button. Next, you have to do your birthday and pick your gender and your country. Depending on your age, it might ask you your parents' email. So so please have your parents with you and tell them to type in their email. Hooray! If the screen appears, join Scratch. Then you're ready to program in Scratch. So when the screen appears, just click OK. Let's go. Actually, I use both versions of Scratch. So now let me show you how to download and install the Scratch Offline and how to use it. On this main screen, scroll down, and then there's going to be support, and then click Offline Editor. Then you'll see the 3 steps. First, it's going to tell you to update Adobe Air if you haven't already. So try it, and it's not going to be a mistake. Next, download and install the Scratch 2.0 offline editor. And then a little lower, you'll see the versions of the offline editor. So if you're on Windows, then click on the Windows download screen. So as I said, you have to install this, and then when you've downloaded and installed it, then run the Scratch offline editor. On step 3, you can find support materials and also the instructions. Scratch is actually a real programming language. But here's the difference between like Scratch. Here's the difference between Scratch and Java and Python and like all that. In Java and Python and some other programming languages, you have to type in the words by hand. But in Scratch, there are really handy blocks that actually mean the same thing. So that's why it's made for children. So let's see how a real program looks like in Scratch. Here's one of the main components in a Scratch project. It's called a sprite. Here's how it looks like. A sprite can be any object. You can draw a sprite, you can pick one from the sprite library, or you can even upload it from your computer. Even I can be a sprite. Here's another component, the background. A background is actually optional. In our first projects, we're not going to use it, but as we go through to the more complex projects, then you'll see that a background is actually a really important part of the scene. The next one is scripts, or the comments itself. This tells the sprite what it needs to do. So what a sprite can do, it can change its look, it can move around, it can play music, and it can even speak. They also can react on the keyboard or input on your mouse. They can interact with other sprites, and I'll show you all of that later. So let's look at the command blocks. All the blocks are split in groups, like control, motion, events, and other. Now let's look a little bit how the Scratch interface looks. Here's the full screen mode. Over here you can change your project's name, and then the green flag is to start your project, and the stop sign is to stop your project. But now, let's create our first simple program. Probably every person who makes his first project would probably write Hello World. So let's make our first Hello World project in Scratch. So if you're in the main page of Scratch, just click Create to create your project. Let's use the existing Scratch cat sprite with our program. Now let's go to the events category and drag the when green flag clicked block to your screen. Now let's go to the looks category and drag the say hello block, and then change it to Hello World. Done! Our first project, Hello World, is done. So let's see how it works. Let's click on the green flag. And as you can see, our cat says Hello World. Let's create a more complex program or game. Let's make a program that's called Clever Mouse. The mouse has to get the cheese, but it has to be careful because there are cats and they can get the mouse. So again, go to the main page and click Create. Or if you're already on the project page, then click on File, which you'll find it on the top left corner, and click New. So let's give our project a name, and let's call it Clever Mouse. Let's delete the sprite and start over. To choose a new sprite, if you want to choose it, then click on the Choose Sprite from Library. So when you go to the Sprite Library, you'll see a lot of different sprites that are actually in ABC order, and they're split up into categories. So let's go to the Animals category, and let's start off with the mouse. So here's a good mouse for us, actually. Okay, we have the sprite, and let's start writing the program. So now let's get the green flag again from the category of events. Now let's go to the category control. Then let's drag out the block forever. Forever is actually a really important block, and here's what it does. You can put different blocks in the forever loop, and the forever loop will do this program forever until you stop it. Right now, we want the mouse to complete a program for it to do something forever. So now let's go to the motion category and drag out the go to block. The go to block simply tells the mouse, this mouse, where to go. So we want it to go to the mouse pointer, which the mouse pointer is our computer mouse. Okay, now let's press the green flag and try and see how it went out, how our little script worked. So as you see, our mouse always forever goes with the pointer of our computer mouse. Now let's try to make our mouse smaller. So here's what you have to do to make it smaller. Go to the menu and press shrink. It's gonna have 4 arrows pointing to the middle. Now let's make a new sprite. It's gonna be the cheese. It's gonna be the cheese that our mouse has to catch. Unfortunately, you can't find a cheese block in the sprite library, but that's not a problem. You can draw it by yourself. So, to draw a new sprite, go to the new sprite section and press the second option, which is going to be a brush. Click on the brush, and then a screen will appear, and you can draw your cheese. So here we're just drawing the cheese, and now let's paint the cheese yellow. Actually, it's not going to seem that hard. You just have to press the paint bucket, and then press it, click on the cheese with it, and then it will color the cheese. But if there's a little space between the lines in the cheese, well, not only cheese, like in different sprites, then say the yellow paint, it will go all over. So now let's fix this so we don't have like everything in yellow. So we're just gonna zoom in a little bit, and then we'll finish the line. And also we could erase like part of the line that's out of that we don't need. So please pay attention to the set cost to center option. It's really important because if you have a sprite and you don't set it on the center, if you don't set the center, there's going to be a lot of unknown mistakes because the center is going to be like anywhere. So your sprite would be in places that you weren't expecting it to be. So now since we drew it, you can see it's like too big. So here's how we are going to shrink it. We can't shrink it with the shrink tool that I showed you a little earlier, but here's how we're going to shrink it. We're going to shrink it by pressing. You'll see on the bottom right corner bitmap and vector. So press convert to vector, and then and then click on the sprite, and then there's going to be a square with circles, and then that's how you shrink it. So you can only, also let me tell you, you can only make the program for one sprite. So on the sprite section, there's going to be your sprites that you have. So click on the sprite that you're trying to program, and it's going to be highlighted in blue lines. So that means that you're programming that sprite. So let's program the cheese block. Now let's change the name of our sprite. Let's make the name into Mr. Cheesy. So now let's try to hide the cheese, like hide it from the page, like screen. So we're gonna drag the when green flag clicked, hide and wait, and then we'll wait a couple seconds. So we need to make it show where no one knows where the cheese is gonna be. So we're gonna use the pick random block. So here's how we're gonna use it. We're gonna use it with the set x and set y, or set x y too. So we're just gonna put in the set random block in there, and then it'll set a random place for it. But so I'll tell you more about the random block later. But so we know right now the random block is for something to appear in random places. So we're gonna find the random block in the category for operators. Okay, let's see how it works. Let's press the green flag. Okay, we're waiting 2 seconds. Oh wait, I forgot something. We have to make it show. We didn't do that yet. Let's go to the looks category and then drag on show. Let's try out now and see how it works. I think it's gonna work. Good, it works. Now let's see if it's gonna go in random places. Yes, now let's try out another time. Yes, it worked! Now let's add a little program to the mouse. Let's make it say, like, for example, yay, I got it when it touches the cheese. Now let's use a new little block. It's kind of like it's actually the shape of a forever loop, but it's gonna tell us if something happens, then do something. In our case, we're gonna do if touching Mr. Cheesy, then say, hooray, I got it. Now let's add a new sprite of a cat. Since I mentioned it's gonna try to chase the mouse. Now we're gonna use a new block, meaning saying point towards. Point towards just simply means point towards something. Well, point towards is to look in a direction. And don't forget about the forever loop. Here in the point towards block, click the arrow, the black arrow next to the point towards mouse pointer sentence, and then let's pick something else for it to point toward. Let's pick point towards mouse. Let's try. See, the cat is looking where the mouse is. Now let's add another command for the cat to not just look at the mouse, but also try to catch it. So we're gonna use the command block move steps. Okay, let's try. Ah, the cat is so fast, it's so hard to do the game. So let's make the cat slower. That's better. Now it's better for the mouse. Now let me show you how sprites can interact with each other. That's actually a little bit harder. It's actually broadcasting. Now we need to do when the mouse reaches the cheese for the cat to disappear. That's going to mean that the mouse is winning. So now let's go to the sprite mouse. Be sure it's highlighted in blue, and we're going to add the if then block. It's going to say if mouse touching Mr. Cheesy, then oh, I forgot, we already have an if then block. So let's use this block. Now let's add the broadcasting part to the if then block. Just simply drag broadcast message 1 to the if then block under the say yeah I got it block, and as I said, the broadcast block simply creates messages for other sprites. Now let's make a new message. So where is the message going to go from the mouse? It's going to go to the cat, and the cat is going to read the message, and then it's going to disappear. So we're going to drag the block when I receive message hide cat, then just disappear. Okay, let's play the game. I skipped something in my Clever Mouse project. When I press the stop and then I press the green flag again, the cat won't show up. Maybe you know how to fix this. But so if you know, then try to do this by yourself and write me in the comments. And also, maybe you could add stuff to this project. In my next video, we'll improve this project and add more cool stuff to it. So in this video, we learned with you how to start with Scratch, how to make your first Hello World program. Here are the blocks we learned. Green flag to start off your project. Another really important block, the forever loop, which simply just tells the computer to repeat a program all the time. You can put different blocks in there, and then the forever loop will make the computer repeat this code. We also got familiar with this block, point towards. The hide and show command just tell the sprite to hide and show. Set X and set Y commands mean where the sprite should be. Later on, we'll stop on this XY thing and we'll learn what this actually means. But right now, just remember the block. Another really important statement: if something happens, do something. You'll be using this a lot in programming. Broadcast. Broadcast means a sprite sending a message to a different sprite. This is really important, and it allows the sprites to interact with other sprites. So if you like this video, press the like button, subscribe if you haven't, and also please see my previous videos, programming intro and how to program. Bye, see you in my next video with Zacky Wack.
Now, activity 6 is for you to design a game through a Scratch program. I would like you to design the same game as Zach did in the tutorial, the clever mouse chasing cheese. So I would like you to register online. It's free. And do your own game. Create your own game. Scratch Online is for ages 8 to 16, but used by all ages, so you're going to enjoy this one. So how do computer scientists think? So thinking one is the input results in an output, or there's always a cause and effect. So for you personally, you actually don't get baffled by problems if you think like a computer scientist, because you would know that to change your output, to change whatever is happening in your life or in the problems that you're facing, you just need to change the input. Thinking number two, that's something good that we can get out of computer scientists, is that there's a language and a translator to every process. So you got to understand it. And I think as well for human beings, with your friends, if sometimes you don't actually get along with someone, with your classmates at this point, you just need to figure out what language and translate, the language that they use. By language, I mean, the personality and the key difference of your colleague, of your classmate. So if you try to figure out the language, then you're able to translate it, and then you're able to actually understand. It's a more peaceful way of surviving that way. And then thinking three is there's a gate to every objective. Remember the logic gate a while ago, and how the computer talks to you through a Boolean logic. If you understand the key, you can actually open it. If you understand your computer and what gates it uses, then you can actually use your computer, and it will work for you. So activity 7, and this is the final activity. Write your own observation on how computer scientists think. So I would like you to add thinking number 4. All right. How do computer scientists think, and what kind of thinking will actually help you in life if you actually think the same way as how computer scientists think? All right, so that brings us to the end of the session, the end of lesson 1, computer class level 6, 7, 8, 9, and 10. If you're ready to submit your work, you can submit it to cluelesstechie@gmail.com, and I will try to view it from there and grade your scores from there. I generally would just like to see a video or a print screen of your project. So that's that. So see you in the next class. Bye bye.